All right, thank you very much, Danie. And hi to everybody on the meeting. It's great to see you all here. Hopefully we'll have some really useful information to share with you today. It's certainly something that I find very interesting. So what we're going to be talking about is the new Panzer RPS S-1 standard for EME safety, and particularly in requirement to its new limits and its a new requirement for spatial averaging. So in terms of our agenda today, so we're going to look at the, firstly have a look at what I think is the implementation timetable for the new RPS S-1 standard, an outline of changes to the EH and S limits, having a look at spatial averaging implications. Danie is going to give us a very interesting demonstration of a new feature in IXUS for implementing spatial averaging. So we want to make sure that if the standard requires spatial averaging, you guys can actually do it with your IXUS software. And then finally, we'll have a wrap up and discussion. Okay, so let's look at the implementation timetable. And these are just bits and pieces that I've managed to find out by keeping my ear to the ground. So the Panzer press release in the 25th of February this year said that the new standard is now in effect and is expected to be implemented by the relevant regulatory bodies in telecommunications, manufacturing, and health sectors over the coming months. So although it says it's now in effect, it's also indicating that the enforcement of it is certainly going to lag a bit from that 25th of December starting date. I had a chat with Dr. Ken Karapetis from Panzer, who I'm sure many of you know, and he indicated that the NDRP, the National Directory of Radiation Protection Standards, will be reissued soon with a new listing for RPS S-1. Hopefully everybody is familiar with the NDRP. It's an important document because it basically sets out a memorandum of understanding between the Commonwealth and the states and territories about picking up the Panzer radiation protection standards. Having said that, though, Western Australia seems to be the only state to have actually formally signed up to the NDRP. So they will automatically be picking up the Panzer RPS S-1 standard, but the other ones, it's a little bit unclear, but I expect, you know, under sort of a general ethos of, you know, good practice, they will eventually set it up. Now, in terms of the other sort of regulatory area that we all need to be mindful of are WHS obligations, so work health and safety regulations. So, for instance, implemented by Comcare and various state WorkSafe authorities under the WHS Acts. And you would also expect any sort of litigation, you know, from those areas to also start looking at the RPS S-1 as the new source of best practice procedures for RF safety. And the last one, last but not least, are ACMA. And of course, we all know that under ACMA regulations, under the, I've just forgotten the name of it, under the apparatus license condition determination. Sorry, just had a little bit of a fade there. That they have already signaled that they probably won't be updating their EMF regulations until probably about the third quarter of 2021. And I think, you know, for your work as EME assessors, that's probably the most important consideration, because until ACMA formally adopt the RPS S-1, then essentially they're still requiring that you continue to assess to RPS 3. compliance limits. So let's have a look at the differences between these two, between the new RPS S-1 and the old RPS 3. So I've just presented a table here, and so I've got the old RPS 3 reference level limits for power flux density in yellow, and the new RPS S-1's in blue. So starting at the top of the table, one thing that you'll notice straight away is that whereas the RPS 3 had 2 power density or EH&S limits, the RPS S-1 has 3. So you have a whole body limit, which is essentially equivalent to the time averaging limit of the RPS 3. But you also have a local limit. And then on top of that, you have a sort of a local instantaneous energy density limit. So let's have a look at, let's sort of compare those a little bit more closely. So let's, for instance, compare the time average limit in RPS 3 with a whole body average limit in RPS S-1. So if you have a look at the limit values, you'll see that they're identical for the frequency ranges of interest for telecommunications. One of the differences, though, is that the time averaging period for RPS 3 has increased from 6 minutes to 30 minutes in the RPS S-1. That's probably not such an important consideration, given that we often tend to use, maximum power levels anyway in our assessments. But the other big difference is that whereas RPS 3 allowed point spatial assessments, in the RPS 1, it actually mandates whole body spatial averaging of the fields. And that's what I really want to talk about in a lot more detail in our presentation today. The other difference is this new local limit. So this time averaging limit has sort of been split into 2, so a whole body one and a local one. And you can see that the local limit is substantially higher. So it's 10 watts per square meter compared to 2. And so it's about 5 times higher, from about 30 to 400 megahertz. And then when you get up to 2 to 6 gigahertz, it's about 4 times higher. And so that means that it's less stringent. And it also has this requirement for a whole body spatial averaging, over these frequency ranges, except in the reactive near field. So this one, I'm not sure how it's going to affect things, because it is, as I said, it's a local, it is, less stringent. Perhaps one way it could be utilized is that if you, for instance, were doing an assessment of an antenna, and you could work out just by power that you could never absorb more than the required, a whole body average SAR level. So, so say, for instance, you had say a 5 watt, source, and it was going, and you were looking at, say, a 100 kilogram person. So, so that would mean, that you couldn't exceed the whole body average SAR limit. So that means that you could forget about complying with the whole body reference level limits, because you've already satisfied the whole body SAR. In which case, you could use the less onerous, local body limits. So that's something to think about. Now, the third one here, the incident energy density limits, they're complicated. I was going to talk about them today, but I thought perhaps better to leave that to a later talk, because that's really a whole topic in itself. I don't think it's going to have an impact. It certainly won't have an impact for sources where you assess them at full power, but maybe for 5G sources where we maybe using a time averaging factor, to account for the movements of beam steering antennas, then perhaps this might actually come into play. Still thinking about that, but we'll talk about that in a later seminar. Okay, so I'm going to get back to this point I read about the RPS S-1 requiring spatial averaging. So I've just copied some text from the standard. And so this is for the whole body reference level limits in table 4 of the RPS S-1. I hope everybody's read it by now. But if you turn to table 4, you'll see it has a note that says that the power density, incident power density, E and H, are to be averaged over 30 minutes over the whole body space. So this is actually a requirement now. It's not an optional. Previously the RPS 3 said you could do spatial averaging if you wanted to, and it kind of left it up to you. But now it's actually mandating it as part of its definition of the reference level limits, and that's something that's been copied from the ICNIRP guidelines, the new ICNIRP guidelines. It also has a note to say that temporal and spatial averaging of each E and H must be conducted over the relevant square values. So what they're saying there is that when you do your averaging, you're not averaging E values, for instance, but you're averaging the E squared values at every averaging point. In terms of power density, it's just the S values, because they're effectively a power term equivalent to E squared. For the local EH and S reference limits, there's in table 5, again, we have a very similar note where it requires that S, E, and H are to be averaged over 6 minutes, and where spatial averaging is specified in notes 6 to 7 over the projected body space. Then later on down in the notes, it defines what that projected body space is. So from 100 kilohertz to 30 megahertz, the projected body space is the whole body space, and likewise from 30 megahertz to 6 gigahertz outside of the reactive near field. Now, the reactive near field is really so close to the antenna, a matter of centimeters, that essentially it's requiring you to do whole body averaging really over pretty much everywhere around an antenna in that frequency range, 30 megahertz to 6 gigahertz. Right, now, one thing that the RPS S-1 doesn't provide is a recommended spatial averaging scheme. It just kind of leaves that floating. So it's kind of left up to the assessor. And that's an important point, because how you assess your spatial averaging has quite an impact on what the compliance zone will look at. Now, in our AS NZ 2772.2 standard for doing EME assessments, it refers to the IEC 62232 standard in terms of recommended spatial averaging schemes. And I've just displayed this, and this is a copy from some work that Steve Iskra presented quite a few years ago now, probably 5 or 6 years ago. And anyway, so what you can see is they have these sort of they're sort of vertically averaged schemes, but they're not actually averaged over the entire body space. So they have averaging points that are sort of around the upper body, but not the lower body. The other thing too is that in some of these 9-point and 6-point schemes, they're actually really hard to implement, because the value that you get from that averaging not only depends on where you actually measure at the points, but also how you orient the points. So, so for instance, if you're facing the antenna, I mean, presumably you would sort of orient this so you're facing, these points are sort of facing, the plane of it is facing the antenna, but you may have multiple antennas. So how you actually orient it, becomes quite confusing. So these schemes here are really quite useless for complying with the new RPS S-1 and indeed the IXUS limits. They're just not practical, and they don't comply with the requirement for averaging over the whole body, projected whole body space. This one here, the 2 meter one with the 20 points, yes, that does comply. And it's doable because, you've got points in a line, but boy, averaging over 20 points is quite an onerous thing. It can be done, calculation wise, but it's really going to slow down the calculations. And then lastly, the RPS 3 had a recommendation, from the old standard. And that was that you found the peak value and then you took an average at plus or minus 1 wavelength above and below the point. And again, that's difficult, very difficult to implement, because if you have multiple frequency sources, then what's lambda? So yeah, not a particularly helpful or practical averaging scheme. So what I'd like to propose in the next slide is some better averaging schemes, and I've called them the 2 meter Peter schemes. And these are based on a projected body space over 2 meters. And so looking at either a 3-point average, so at the top of the head, in the middle of the body, and down at the bottom of the body, or a 5-point average, where we have at the top, around the chest, around the middle, around the knees, and down at the feet. And these schemes, I think, do comply with the intent of the RPS S-1 and IXUS guidelines. They're over the projected body space, and they're relatively straightforward to implement as well. So now in the next slide, I'm going to show you what the averaging schemes actually look like when you implement them. So here in this slide, we have what I've modeled is an antenna. So this is hopefully you can see it. There's a panel antenna, and it has the gray zone is the zone that you would normally expect from our current practices, where we're using a point spatial assessments. And the blue zone shows what that compliance zone would look like if you did 21-point spatial averaging. And you can see it really does make quite a difference to the size of the zones. So looking at, for instance, in the side view over here on the right top panel, you can see that the 21-point spatial averaging is certainly less in extent out in front of the antenna. And if you have a look in the bottom, it's also less in extent, to the sides as well. However, there is a trade-off. You can see here again in the top panel, in that the extent of the compliance zone actually grows in the vertical direction. Likewise, if we have a look at another example, this one's even more striking. So this is for a Yagi antenna. So you can see the green 21-point spatial averaging compliance zone, and here we have the blue one is the point spatial, and you can see just how different they are. You can see that in the top view. So like in the previous example, I showed the horizontal extents are less for the green 21-point spatial averaging compliance zone, but the vertical extents are bigger. So this kind of really introduces, just sort of looking at it on face value, sort of produces a bit of a difficult problem, because it's saying that potentially the new compliance limits with spatial averaging of the RPS S-1 can be either more or less stringent. And so that kind of puts a bit of an urgency on, when you actually start implementing the RPS S-1 compliance standards, because, you know, someone might say that, you know, you did it to the old RPS S-1, but, you know, I was below the antenna, and, you know, according to the new, you know, the new standard, you know, I could have been overexposed. I'm going to talk a bit more about that later, though. I don't think that's actually going to be a problem, and I'll show you why in a couple of slides later on. Okay, so this slide, again, it's kind of a bit of a rehash of the slide I showed you earlier with the base station antenna. But in this case, I've actually added a few more different compliance schemes over the 2 meters. So the orange one is the 3-point 2 meter averaging scheme. The purple one is the 5-point, the green one 11-point, and this blue one is 21 points. If you have a look at it in side view at this top right-hand panel, you'll see there's, you know, a kind of a trend. So the orange 5.1 has got the smallest zone, you know, in terms of front to back, and also to the sides as well. But it's got the highest vertical extent. And then as you start increasing the number of averaging points in your scheme, you know, it starts to head a bit more towards a point spatial. Never quite gets there. And of course, you get to a point where no matter how many spatial averaging points you include, they just kind of tend towards a kind of a limit value here, which we can see around the 21-point averaging scheme. All right, now here's this is what I was referring to a little bit earlier, and about interpretation of the new RPS S-1 or IXUS compliance zones. So what I've drawn here is the you know, the standard point spatial compliance boundary that we're all currently using. And then the purple one, we've got the 2 meter 5-point spatial averaging compliance boundary. So up until now, the way that we've interpreted compliance boundaries is that it's sort of in a peak limit sort of mode. So basically, we're saying that you cannot put any part of your body into that compliance zone, because if you do, then you're considered, you know, to be non-compliant with the limit. And so you can see in this particular example, if you reassessed with the 5-point spatial averaging scheme, what was previously compliant for this guy here, this guy here, this guy here, and this guy here, is no longer compliant, you know, with the new 5-point spatial averaging boundary. But actually, I don't think that's the case, and I'm going to show you now in the next slide why. And the reason why I don't think that's the case is because when you do a 5-point spatial averaging, your assessment point is basically at the center of the body. Okay, so I've now drawn, so these new guys that have come in, they're guys that are basically right on the edge of the compliance boundary for the 5-point spatial average compliance boundary. And so if you have, if this guy here is a little bit lower, then he's okay, because his assessment point, it's not at the top of his head, it's actually in the center of his body. So in that case, when you do spatial average compliance assessments, the compliance boundary is going to shrink in every direction, not just in the lateral directions, you know, forward and back and left and right, but also in the vertical direction, if you take, you know, this interpretation of spatial average compliance. So that's good, in that it means that that sort of takes the pressure off, you know, sort of moving over to the new RPS S-1 standard, because the old standard limits, assuming this interpretation, are going to be more stringent than the new standard limits. So everybody's going to be fine. However, of course, if you want to take advantage of, smaller compliance zones, then definitely hop on over to the RPS S-1, when the regulators give the okay. Now, another thing I'd like to show you, this is an idea that was actually suggested to me by Brendan Woods. So thank you, Brendan. And this is about using the lobe imprint for compliance. So as you know, IXUS has a lobe imprint functionality. So it basically draws, red or yellow zones. If somebody's standing on the surface, standing on the ground, where they can actually stand on the ground and where not. So again, I've drawn the two compliance boundaries, one with the 5-point spatial average and one with the point spatial. And you can see all of these guys, because the assessment point is at the center of the body, all of these guys are actually okay. So in this particular case for 5-point spatial averaging, there wouldn't be any lobe imprint. But if you're using the old point spatial compliance boundary, then you can see that the lobe imprint, this guy's head starts to get into the gray area, would probably extend out to the length of this red bar here. And so Brendan's idea was that, rather so much on focusing on, showing compliance zones from the antenna, he thought, in a way, it's actually kind of more useful just to show the lobe imprints on the ground, because they kind of is easier to interpret for people, say, wandering around the rooftop, so long as they're not, climbing up an antenna where they might, pop into a compliance zone of an antenna overhead. So anyway, so something to think about there. Okay, now in the next slide, I want to talk about spatial averaging validation. So I said earlier on that RPS S-1 doesn't really give any clues as to what sort of spatial averaging scheme you can use. And but nonetheless, there's sort of like a general, requirement that if reference level limits should always ensure that if you comply with the reference level limit, then you're also automatically complying with the basic restriction limits. So the basic restriction limits for the EH and reference levels are local SAR, or local 10-gram SAR, and whole body SAR. Now, what I've produced here is a copy of a slide from that was presented by Steve Iskra from Telstra back in 2015. And what he did was a really interesting study. So what he did was he developed a FECO model. This is a full wave model of a base station panel antenna. So you can see that here on the left-hand side. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9 little dipole elements with a backplane. And what he did was he calculated the, using FECO, he calculated the whole body SAR in a model at various distance, from the front of the antenna, sort of moving along the bore side main lobe beam. And then what he did was he plotted this out on a graph where he plotted the level of percentage compliance with the RPS occupational exposure limit versus a separation distance from the antenna. And so, for instance, with this blue line, the 10-gram line, you can see that when you're about 1 meter, out from the antenna, you're about 60% compliant, with the 10-gram SAR limit. And then as you go, further up and up, say to about, I don't know, 0.3 3 meters away from the antenna, you'll basically hit the 100% limit, and that's as far as you can go according to the whole body, the local average SAR limit. And likewise, you can see he's done the same for whole body SAR as well, and that's shown by the red curve. Then what he did, which is interesting, was he looked at what the compliance curves were for spatially averaged fields. And so what he looked at was those IEC 62232 recommended fields that I showed you a few slides previous. So you've got the 20.1, the 3.1, a 6.1, and a 9.1. And he also looked at the peak field as well, which is kind of what we're using at the moment. And what he found in all those cases was that the spatially averaged fields were always less stringent than the basic restriction SAR compliance curves. So what that's essentially saying is that spatial averaging reference level fields will always be fine as a proxy for the basic restrictions. You'll always be compliant with these whole body, the SAR basic restrictions if you use the spatially averaged field assessment methods for EH&S. He also compared his data to, I'm just going to show these curves as well, where he compared calculation formulas in a very interesting paper by Bjorn Thorn and his colleagues at Ericsson, and also colleagues at AlphaWave as well, who contributed to a study where they developed these simple, well, fairly reasonably simple, not that simple, but they're reasonably simple formulas for calculating whole body average in SAR and local SAR along the main beam of an antenna. And you can see again the spatially averaged fields are also compliant, with the Bjorn et al. SAR compliance curves as well. So all good. So that's looking terrific. That gives us confidence that the spatial averaging fields are okay. And he did also repeated the study, sort of looking off bore side as well. And again, that turned out good. The spatial averaging field compliance curves were well above the SAR restriction compliance curves. However, I actually tried to replicate Steve's work, and I ran into some problems. So here's what my compliance curves actually look like. So the blue and the orange are the SAR, whole body and 10 gram local, restriction curves, basic restriction curves. And you can see there's the orange one there, and there's the blue one. And then what I've done is I've plotted the compliance curves for the 3-point average, 5-point average, and the 21-point average. And you can see in pretty much all of them, except the 21-point average, they're not necessarily more stringent than the basic restriction curves. So that's a bit of a bother. I'm not quite sure why that's the case. So I'm still ticky-tacking with Steve about, obviously, one of us has made a mistake. We're not quite sure which, but that's something that, we need to keep looking into. So I'm going to have to pull back my enthusiasm and optimism from the previous slide and say, this is something that we need to think a bit more about. One thing that it does say to me, though, is that calculating this stuff can be complicated. And also it says to me that it's really important that we get, some checking by some independent people as well. And that's something that I would put to you, dear EME assessors, as you are all certified as independent assessors. under your NATA accreditations, you do actually have an obligation to check all the tools that you're using, including IXUS. Not that I think IXUS is wrong, but I think nonetheless, it would probably be helpful. It'd be a good idea if you did. And I think it'd be instructive for you as well, because you probably learn to understand more about what's happening under the hood. And IXUS has, functionality that will allow you to do these sorts of checks, which we can talk about later. Okay, so I think at this point, I'm going to hand over to Danie, and I'll let him do a demo of the new IXUS feature. So I'll just stop share.
Thank you. I appreciate that very good overview, Vitas. So I'm going to start sharing my screen. And it should take, I'm going to stop my video just to improve the speed a bit on my side. So, okay, so can everybody see my screen now? It should be similar to what Vitas just showed. With,
yeah, I think so.
Okay, everything fine. All right, so I'm not going to discuss the technical details. Vitas already covered that in detail. So this focus is now more on telling you a bit about the implementation of the 3-point averaging schemes in IXUS, the various spatial averaging schemes in IXUS. So we have introduced essentially 3 methods with that our users can make use of, or in the IXUS modeler, to apply spatial averaging to the calculated results. And the first of which is essentially sampling the entire exclusion zone, or the plumes, using a preset number of sampling schemes. Now, the first scheme that we introduced was this one from the IEC 62232 standard that Vitas also mentioned in earlier slides. Is essentially sampling the space of the upper torso of a person. So we used to call this guy Jeff, but now we've got to switch to calling him Peter as a result of introducing the other 2 schemes, which is now this 3-point and 5-point schemes, where we sample over the whole body projected area, which is 2 meters in our case. This one being a 3-point averaging. So when we evaluate the field in a 3D space, then we also evaluate the field 1 meter above and 1 meter below that point. And with the 5-point scheme, it's this 2 meter region is just divided into 5 equally spaced points, separated by 0.5 meters apart. Okay, so this is what we call our global averaging scheme, and what it does is, and I'll show you now in demo, is it essentially modifies the entire 3-dimensional exclusion zone for you if you apply this scheme. And the trend that we are noting, as Vitas also mentioned, is that in bore sight from the antenna, the exclusion zones decreases slightly when you apply the spatial averaging, yet it increases vertically as well.
Actually, Danie,
yes.
Another thing to notice in that slide is that with the IEC scheme, the boundary compliance zone are not symmetrical.
Yeah.
Which kind of really doesn't make a lot of sense. And again, it kind of underlies, the reason why those schemes are just not very useful.
Yeah. So that's a very good point to note as well. So the other, that's why I think these, say 2 meter Peter schemes makes intuitively and physically makes quite a bit of sense. They are symmetrically sampled, so we don't expect this type of asymmetry artifacts as a result of the spatial sampling, spatial averaging. Okay, so this is 3-dimensional spatial averaging, which I'll show you now how to set that in the IXUS modeler. The other method that we've introduced is we've extended our field point widget. In the past, it only essentially, if you sampled the field using a field point over a specific range, you have a start time and a range, then what it returned is the maximum value of the field in that range. Now, that will still be the case, but in addition to that, we've also allowed this average value calculation type setting. So when you set that, you can actually say, okay, in this range, it starts from here to there, I want to subdivide it into this number of vertical spacings, and that will result in a number of samples, which I can then sample along this vertical line, and then we just report at no particular point the average of the field in that region. So this is now for our field point, where you can essentially apply your own sampling scheme or comply with something like the 21-point sampling scheme. And computationally, it's not very expensive, because we refrain our calculations to the single vertical let's say region, and not the entire three-dimensional space. We've extended the same type of ideas to our environmental ortho slice as well. So with our ortho slice, and I'll show you now in the IXUS model how that looks, you can essentially also calculate the fields anywhere on this environmental ortho slice plane as the result of the sampling that extends from the top of where you place the environmental frame, the environmental slice, all the way down on a particular range, and you then also subdivide that range into the number of spacings that you want to get the samples. This is computationally, this is slightly more expensive, because we have to essentially, when we calculate 1 point, it's not just 1 point calculation, it also extends for a number of samples downwards, and same for every other point in this environmental slice. So in my demo, I'm going to use a very trivial antenna, or not trivial antenna, but an antenna that was actually supported in the IEC 6232 document to be used as a reference antenna. So this antenna, as I've added it to our IXUS portal as well. So anybody doing independent assessments is also welcome to go and grab it there, import it into IXUS, and then you can simulate it, and you can then independently verify that the zones you get is actually compliant with documentation such as this. This is just a bit of detail where this antenna model comes from. This is the full wave FECO model. And then this was a comparison actually done by Dr. Vitas in 2020, where he compared our IXUS model results with FECO, and it ties up quite nicely, as expected. Okay, so what I want to do now is show you our IXUS modeler and very quickly demo some of this functionality and where you would set it. And also, more importantly, note that this is a beta release, so it's not yet released. This will be coming out in our IXUS 2021.1 release, which we hope to have done in the next month or two. As we've also been discussing it with a lot of you in our client feedback meetings. So, a disclaimer: if something crashes all of a sudden, I apologize. It is beta software. It's currently still being tested, and bugs do creep in, and bugs also do creep in more regularly when you do demos. So I ran through it, but please bear with me. Okay, so first thing, we're going to add our IEC model, no tilts. I'm just going to give it 90 watts of power on each of the ports, and it's simulated at 900 megahertz. So we're going to place it here, just on the ground marker. Very simple structure like this. For the sake of illustrating the features, I'm not going to add buildings and geometries and all these things. I merely want to focus on the fields and also on the sampling of the fields. Okay, so first thing is, for those that have not seen, in terms of dimensioning, we've also added a bit more functionality. So we've actually added this three-dimensional grid, which can be used to dimension things a bit nicer in IXUS. So you can set its width, you can set its depth. Now these are all things that I calculated a bit beforehand, because I sort of looked at the compliance zones. But obviously you can adjust this after you've simulated your antennas or multiple transmitters or geometries and so on. The grid's fairly versatile. Okay, what was my, okay, so now I have my grid placed here, but before that I should actually simulate my plumes. So the first thing I want to show you is the just the standard point spatial simulation. So let me do this again. So under our preferences and general options, we've now added this additional setting here called calculation options. And this is now denotes which spatial averaging scheme you will be applying to the entire three-dimensional space when we calculate the plumes. So at the moment, we only have the 3-point IEC scheme, but we'll add the others as well in due course before release. So the point spatial simulation, if I just run it like this, is essentially generates the results that that you are used to. I think I swapped this around. Let me just see here. Yeah, that should be, that makes a bit more sense, right? Okay, so here's are my plumes. These are the standard ones that you're used to. If I now go over to a 3-point moving average and I simulate it again, then essentially my exclusion zone geometry changes slightly. So yeah, so this is the on the global side of things, how you can simulate these exclusion zones. We've also introduced, as I said, the point scheme sampling. So let me just add it at a particular point here, for example. Okay, so with this, you can just select the field point widget as you would per normally do. Oh, the other thing now is that you'll see this calculation type is grayed out. So the reason is that I don't want to apply a spatial averaging on this local field point while I still have a spatial averaging associated with my original 3D plume calculation. Essentially, you'll be applying an average on an average. So in order to do that, you need to have your global averaging scheme set to point spatial so that you can then go ahead and apply local averaging on your field point over here. Okay, so the maximum simulation is just as you would have simulated per normal, indicates where the maximum is located in this range with this particular percentage value. This is now percentage of standard. And the only thing we've added is this clarity that it says max here on the side. So likewise, I can now switch to an averaging scheme and I can say, okay, I want to average at 0.1 intervals here, and this will result in 21 sampling points. And then I can run it again and my results are returned as a percentage, but here I can clearly see that it's the average. And there's no particular point because the average is applied in this entire region. All right, so, oh, sorry. So this is my field point spatial averaging scheme, my global spatial averaging scheme, and then finally, I would like to show you the environmental orthoslice scheme. This one, I'm just going to hide that. And just to make my life a bit easier, I'm going to add a marker where I would want to place it. So let's say I want to place my environmental slice. So this is the slice as you would know it. I'm going to place it there. I'm not going to give it a particular offset. I just want to calculate the fields on that plane and indicate the maximum as well using our point spatial simulation method. So that would be the calculation that you've done as per normal. So let's just show and hide that as well. Okay, so this is my point spatial simulation. What I can then do is I can do exactly the same thing. using spatial averaging. So if I switch to spatial averaging, I can now say, okay, from this plane downwards, I can subdivide my sampling into this value that I have. So here's just 0.1. I can still calculate the maximum in that region also. That 0 should not have popped up there. That's an artifact of this being a beta release, which we will obviously correct. And now it calculates. And as you can note, this calculation takes longer, and the reason is because the field calculations is just much more. So in the next release, well, the focus towards the end of the year is to improve also our efficiency, our computational efficiency, by applying things like GPU acceleration to the calculation as well, and other methods for accelerating the calculations. Okay, so as you can see here, if I just, this is now my spatially averaged environmental slide with my maximum still shown as we expect in the balls that I have the antenna, but this value has reduced a bit now. Okay, so those are the 3 calculation methods in IXUS that we are currently implementing to ensure that when the new RPS S-1 standards comes out, you guys are ready for it, because we supplied you with the necessary tools. Yes, and I think over to you again, Vitas.
Okay, thanks, Danie. And I'll take over the share screen. There it is. Great. All right, I'm back in control. Yes, thanks very much for that.
Vitas, you just need to skip to the right slide. I think it's slide 23 or so.
Hang on a second. I think I might have clicked the wrong app.
Hi, Vitas, sorry.
Hi, Johan.
I just wanted to comment that we were typing some questions in the chat, and
Yes,
Chengli
yeah, I saw
asked me
those.
which one it is, but I made it 0.20 minus 0.4. Can you just quickly go to the slide where it shows which one we implemented, that IEC slide?
The IEC slide, yeah.
Because I think I might have confused them now.
All right. Sorry,
so
can you see my can you see that, by the way? Can you see my screen?
That 3.1, the third one from the left, Chengli, that's the one that we implemented. Oh, sorry.
Right.
Well, the one on the left there as well.
But Chengli, it's important to note we'll add the others, which makes physically then you have the options to select.
Okay. Thanks for that clarification, Johan. Okay, so we're getting towards the end of our talk now. And so basically, I kind of leave you with a couple of questions. I was hoping to be, wanting to be a bit more definitive, but unfortunately, things are still a little bit fluid at the moment. So first question was when to apply spatial averaging in your assessments. And I think at this stage, it's probably best to wait until ACMA actually formally adopts the RPS S-1 in their apparatus license condition determination. And I say that because I think, I'm not 100% sure, but I think that the new RPS S-1 will always be less stringent, even with spatial averaging, compared to the old RPS 3 with point spatial fields. But I'm not totally sure about that, but I think it will go that way. The other question was what sort of spatial averaging scheme to pick. Well, definitely, we would, you know, at IXUS, we would definitely recommend a vertical line. So not some kind of plane, you know, where you've got points on either side, because it's just impossible, you know, to implement, you know, if you have multiple sources, because you don't know where to orient it to. Also, terms of size, we're recommending a 2 meter length, the 2 meter Peter. And the reason for that is that 2 meters sort of covers, the taller, size, of the human population. And then in terms of number of averaging points, probably 3 or 5 would be recommended. But again, that depends on just how well the spatial averaging for those 3 or 5 points, ensures compliance with the basic restrictions. But 3 and 5 are a good number in terms of, computational efficiency. So that's just something that we need to look into a little bit more. So sorry, I couldn't be more definitive about that. But at least hopefully you've got an understanding of the issues and what's coming down the track with this new RPS S-1 standard and its spatial averaging requirements. Okay, so I think that's pretty much at the end of our talk. We're just on the hour, but if you'd like to hold on, we can respond to some questions now. So,
Vitas, can I highlight the first one, which I think would be very exciting for you, asked by Brendan from Oricon. So Brendan asked, should this be part of the uncertainty?
No. Brendan, why did you ask that question? No, I don't. No, I don't. And the reason I don't is because uncertainty is meant to cover things that are, variabilities in your assessment, that you just can't pin down, accurately. But spatial averaging, spatial averaging is actually part of this. It's part of the assessment definition. It's the assessment itself. If you say, I'm going to spatially average, vertically over 5 points, that is how you define your assessment. You don't have to apply an uncertainty for that. It makes no sense. It's like saying, my definition of the assessment was to measure E field. Okay, if you measure E field, then don't try and come up with some uncertainty for how that different, how that's different to the H field, for instance. If basically spatial averaging is part of the definition of the assessment, then it's not an uncertainty. So yeah, I hope that's very clear. As much as I love uncertainty, as you all know, it's really not part of the uncertainty assessment. Actually, another thing too that does bring something else to mind, though, when you do start implementing these new spatially averaged fields, be sure to actually describe that, in your reports, because as I said, that's how you're defining your assessment. So, if you use a 5-point vertical 2 meter spatial averaging scheme, put that in your report, because that's a very important piece of information in terms of interpreting reports and replicating, your assessment as well.
Hi, Vitas. Sorry, can I just mention something here? So what we're implementing as well is an indication of what was used, which scheme was used on the pictures.
Oh, great.
With the content controls. So it will be very clear.
Excellent.
Which one was used. There was a question from William here that's very interesting, that you might have a better.
Yes. So was that the one about the lobe imprint?
No, the last one.
Oh, hang on a second.
William, you're welcome to unmute also if you want to ask.
William,
yourself.
just ask so everyone knows what you want.
Yeah.
Hi everyone. This is Will from Nokia.
Hey, William.
Hi, how are you?
Yeah, good, thank you. Yeah, thanks for your question.
Yeah, I just got this question. So I saw that you were changing the settings in IXUS before you simulate the plumes. So I was just wondering if in the future release we can change the setting, how are we going to control that everyone's using the same settings? Because we are definitely not assessed on Nokia, or so we're doing PIDs. So how are we going to make sure that when it comes to the assessor stage, the assessor are going to use the same setting as us, so the result will be consistent.
Well, that's something that you know, you have to tackle, you know, under your quality control systems. So, you know, as I was saying, when you do an assessment, be very clear that you document that and you make that, you know, the details of your assessment technique, you know, very clearly specified on your reports. And, you know, if you want to have consistent assessments with other assessors, then really you need to get together, you know, with those other guys and actually agree on a preferred technique. In fact, actually, it really does raise a very good point, William, you know, in terms of, you know, all of you, you know, sort of coming together and deciding, you know, on what you're going to do, because, you know, there's always safety in numbers. If you're part of the bigger group, that's always a good thing in terms of credibility. So I would recommend, you know, that whatever forums that you get together in, maybe maybe RFAG, the RFSS's Guild, maybe this would be a good thing for you guys to discuss and make sure that you move forward together, you know, as a coherent group, so that, you know, that stops any potential disputes, you know, between different assessors, because of course you will get different results, you know, if you use a different assessment technique.
But Vitas, sorry, this is Austin here. So
Hi, Austin.
the problem is that, yeah, so Nokia, other vendors, carriers, we are not in the same boat here. So we are doing preliminary assessments with the technique, and then the assessor does something different. We cannot, you know, tell them you have to use this technique or the other technique, because they are independent. So this comes down then to a problem where, you know, how do we all agree on what's the best option? You are giving us two options. Yeah. There's another question: why two options when one perhaps is more accurate than the other?
Well, it's not a matter of one being more accurate. It's really a matter of one being more appropriate than the other. You know, if I mean, at the moment, RPS 3 is more appropriate because that's what ECMA are still, you know, requiring, you know, in their regulations. But when they switch over to RPS 1, then that's the appropriate one that you have to do. You can't just keep going along with RPS 3, you know, if the regulations have sort of clearly indicated that the RPS S-1, you know, is a requirement. And, you know, as I was explaining, spatial averaging is, you know, a mandatory feature of the new reference level limits in RPS S-1. Yeah, so I guess that would be my advice. I mean, you know, as a client, you know, if you're a client for assessors, you know, you're also able to specify to your assessment team, you know, what you know, some of the parameters of the assessment as well. So
I'm not too sure about that.
Well, I mean, as long as they don't, you know, compromise, you know, the integrity of the assessment. Yeah, but you know, this is an industry sort of discussion, you know, that has to go ahead. And to be honest, you know,
that's something that I think NATA should be involved in this discussion.
Yeah, and frankly, I'm really surprised that this hasn't happened already. I mean, we know that you know, RPS S-1 has been coming down the track, you know, for quite a while, and it's out now. So really, you know, the time for discussing this is now. You know, I think that you know, whatever forums, you know, you have, you know, to get together as an industry, you really need to start utilizing them now. I mean, if you like, you know, at IXUS, we can help to facilitate that. You know, we can help to arrange, you know, Zoom calls, but you know, we'll leave that up to you.
This raises a lot of issues. I think the carriers should discuss.
I have a question, Vitas.
Yes.
So if you increase the number of points you average, so is it will increase the accuracy? I mean, when you mean the whole body?
Yeah, accuracy. That's a very good question. As I said, accuracy is probably not quite the right word. You know.
Yeah, I mean compliance to the standard. I mean,
yeah. Well,
so
I think
the standard mean the whole body, but I mean it's very broad. The whole body, but it's very broad. So
yeah.
So if you increase the number of point we calculate to the infinity, would be more
accurate? No.
Not accurate, but it's what more complies to standard.
Yeah. Okay. Well, I think to me the key thing is to ensure that whatever averaging scheme that you use, if you use it, then you will also be compliant with the basic restriction requirements. So whole body SAR and localized SAR. So if a 3-point scheme is enough to ensure compliance with a whole body SAR and localized SAR, then that's fine. That's it. You could use that. And it doesn't matter if you use a 5-point or a 21-point. All of them are appropriate. But once you satisfy the requirements that your averaging scheme is ensuring compliance with the basic restrictions, then you can use other criteria, as to which scheme you might use. So if, say, for instance, a 3-point scheme is fine, then why would you pick a 21-point scheme, when that's going to introduce a computational overhead? So, and in terms of accuracy, well, if you define your measurement as a 3-point average, that's it. That's part of the definition, of the scheme. So comparing it to a 21-point average is kind of meaningless, because that's not what you're actually setting out to do. You've actually defined your assessment in a particular way, and that's the end of the story. Did I answer that question, Owen, or?
Well, I'm not quite sure, but my feeling is that if you choose like 3 points over 2 meters, Peter, is it like, if I feel like it's less accurate, it's less, the result you return would be farther to what's the spatial, the point we have at the moment. So in another word, the shorter Peter or more point you chose, it would affect the size of the plumes. So,
yes, it does. Yeah, definitely. Yeah.
So in the end, it's like it comes to the point. So which one would be?
I just wanted to comment here. So what we're going to do is implement various of these schemes. So what you could do is start with a 3-point, and if you see problems, you can move over to one with more points, which will take longer to calculate.
Yeah,
that's what I would do.
Yeah. Okay.
Yeah. Well, but as I said, so long as your scheme ensures that you comply with the basic restrictions, it doesn't matter. When you talk about accuracy, it's kind of a meaningless concept in that you're not trying to be at like an infinite number of points. That's not the aim. The aim is just to pick, to specify an assessment technique that satisfies, the requirement of ensuring that you satisfy the basic restrictions. That's it. That's all you need to worry about. The rest of it, then the rest of it just comes down to practicalities. So, you could go ahead and do a 21-point scheme, but that's just going to, increase your computational load for no gain, because if both the 3 and the 21-point satisfy basic restrictions, there's no gain in doing a 21-point average.
And I think, Peter, sorry. Yeah.
So do you mean? Sorry. Go ahead.
I think we're getting off track here, because I think the whole idea of having a 3-point system, or trying to simplify the computational, is actually to define the exclusion zone boundaries. So we're trying to find a boundary. Again, as we recommend regarding lobe imprints in areas where it may be accessible by others. Then you can do a spatial averaging over any height you want, whether it's a 1 meter person or 2 meter person. Then at that point, you should be able to do multiple calculations. If you've got 21 points, fine, you can do that. We'll do 3 points. But to define the limit boundaries, 3 or 5 is sufficient.
Does that answer your question, Owen?
No, I'm just trying to understand here is that do you mean that because the way we equivalent from basic limit to the reference limit is very safe in a very safe way. So that's why we
absolutely.
That's why we can kind of like relax in the way we apply the schemes. Is that the reason why you said?
Yeah, but you know, I mean, I guess what I'm trying to put out is that once you're compliant, you know, with a limit, you don't have to over comply. You know, once it's like an all or nothing. You know, so if you have a spatial averaging scheme that ensures compliance with basic restrictions, that's it. That's all you need to do. You don't need to go any further. I mean, you can go ahead further if you want to, but then you're just sort of adding unnecessary, you know, factors, you know, to your assessment that are just going to make, you know, that are just not necessary. Yeah.
Oh, yeah, but probably in terms of application in industry, as one of the guys mentioned, it could be an issue for us, because if the different assessors choose different schemes, it might cause a different result. And
Yes.
because, you know, we also work under different guidelines and safety, and then they are quite strict on that, and then it could cause some sort of like you might say that unnecessary mitigation or some sort of that stuff. So
it
could be very complex.
Yeah,
but
and
in
this
terms
is the
of
point.
application.
Yeah, and this is the point that Austin was raising as well. You know, that you need consistency. Well, you want consistency, you know, between assessors, and so it's really vitally important that all of you get together, you know, as an industry, to come up with an agreed approach.
Yeah, I agree. But do you think that probably in any standard organization would recommend some sort of like scheme how to
maybe.
Yeah.
Look, possibly, yeah. I mean, that would be a job for the TE7 committee for 2772.2 standard.
Yeah.
But you know, that's going to be a very slow process, and you know, this train's already on the track and thundering down towards you, so you need to come with something a bit quicker than that.
Yeah, well, we've got backing by NATO. They said they were part of the organisation the last time we spoke. So, and they provide the support as needed. And other associations will probably be welcome to join us as well. So it's a matter of just getting something organised and organising the assessors together to make sure the industry's got a common approach and a common voice.
Yeah,
definitely. Yeah.
Okay, I think there are some additional questions if I see in the chat, but I hope through this discussion that we've essentially covered it. If not, I'll look through the questions again with Vitas afterwards, and we'll just respond via email, I think. Yeah, I see we're a bit over time, but that's fine. I think it was absolutely worth this interesting discussion at the end. And as we want to summarize, we're not dictating the standard in any way or imposing our own ideas on it. We're just merely providing the tools, right? And in the end, it really is up to the users to make sure that they apply the correct calculation schemes. It's like with any electromagnetic simulation, I can simulate something using various solver settings and get results, but it's up to me to ensure that those results actually make sense. So, and we do our best to verify that we are 100% accurate given this solver that's selected. But as this topic grows in maturity, we will also issue some guidelines, articles, and enhance the knowledge base with it as well to provide our recommendations. And if any, like, we are really all for hearing what you guys think, which road to take. Client feedback is critical for us. It formulates our roadmap, where we put development efforts and research focus. So it would help me a lot or us as IXUS a lot if you can make some recommendations, if you have some great ideas.
Yeah, and look, every journey starts with a single step. We've made a start today, but that's not the end of it. It's really just the beginning. There's still plenty of things to do. Certainly, I'd like to do a lot more validation and verification, but also you need to start organising amongst yourselves as well to start working towards a common, standard approach.
Thank you, Vitas. So Vitas implemented an uncertainty in his answers to make sure that the
always with the uncertainty jokes, Johan.
So I feel that this was very nice to give you more insight in the current state of things, and we would like to confirm that IXUS backs you with whatever changes to the tools is required, and we will implement whatever is necessary. Yeah, so that's the most important part you have to take home from this, and it's a good starting point, at least, right?
Yes.
Great.
Right, then everybody should have a wonderful day further, or evening. I don't know where everybody's joining from in the world. And then, yeah, I'll post this video on our YouTube channel as well, so you can rewatch it if you want, and email us if you have any additional.
Okay.
Yeah, William, sorry, I see you've got a question. Yes, the one at the moment, we've got a 3-point scheme, but we will be implementing the others that Vitas showed, the 2-meter Peter schemes, which is the 3-point and the 5-point for our global average. That answers it.
All right, very good. Well, thanks everyone for attending.
Thank you.
And we'll have some more technical seminars in the future. We hope you found this one useful.
Thank you very much.
Thank you.
Thanks, everyone.
Thanks, Johan and Danie.
Right, thanks, guys. Thanks, Vitas.
Thank you.
You're welcome.
Goodbye.
Bye.
Thanks, guys.